Okay, in this video we're going to look at polarity. Polarity is really important in understanding how intermolecular forces work within a molecule. So we know that the three intermolecular forces that we study are dispersion forces, but the other two are dipole-dipole interactions, and lastly hydrogen bonding, which is a bit like dipole-dipole. The second two here, dipole-dipole and hydrogen bonding, depend on how polar the molecule is. So this is all to do with polarity. So to understand polarity, we first need to go right back to talking about electronegativity. So you can see here the electronegativities of various elements, S and P block elements. And you can see that the most electronegative one is fluorine on this chart here, and that's generally the trend on the periodic table. Is as you go to the right, you have increasing electronegativity, which also goes down as you go up, also increases upwards as well. Increasing. We don't have numbers for this group because they are the noble gases, so they don't attract electrons because they've got a full octet. So fluorine ends up being the most electronegative of all of the elements. Now, that means that the bonds will be affected. So if we look at polarity within a bond between two atoms, the electrons around a perfectly symmetrical atom, so say Cl2, which looks like this. So you've got a chlorine atom and a chlorine atom. It doesn't matter what the electronegativity is there, they are the same. So the electrons are spread equally around the atoms. So we have to remember that electrons are in the bond and they're also around the atom. So they spread around the atom like this, okay, and they orbit effectively in a sort of even distribution. When you have differing polarities, this doesn't happen. So if we look at these examples here, the more electronegative atom on the right, which we show by doing a little lowercase delta negative and delta positive, we can see it hogs more of the electron density. And actually, if we increase it even more so, we can get to the point where it almost completely separates, and eventually it would become an ionic bond rather than a covalent bond. So these ones would be covalent still, becoming more and more polar. So this one's polar covalent. And then lastly, we've got almost ionic, so very polar. Okay, and then the final product would be where you have complete electron transfer. So this is ionic. And so it's actually a spectrum of polarization depending on the difference in the electronegativities. So you can imagine if we had, for example, lithium fluoride, they are so different in electronegativity. Let me just use a different color there. They're so different in electronegativity that they become ionic. Whereas if we have carbon fluoride, so that would be CF4, they're covalent because it's highly polar but covalent because they are not as different in electronegativities. So you would have negative fluorines and then positive in the middle there. So it's a symmetrical molecule, but it would be highly polar each bond. So if we look at a simple hydrogen halide, which is a group 17 element bonded to hydrogen, we can see that if we change the halogen part for less and less electronegative ones, so if you go down the periodic table, they become less electronegative, the polarization decreases. And we know that because the difference in the electronegativity is decreasing. And that has implications for the bonding. So similar to the diagram above, it would become more and more ionic. So in actual fact, the hydrogen iodide is actually a covalent bond. Hydrogen bromide is covalent. Hydrogen chloride easily becomes ionic, and hydrogen fluoride even more easily again. So that's how the polarity works within the molecule. So we talk about covalent character. So covalent character is where on this scale you sit. So a perfect covalent is where they share completely equally, something like oxygen, O2, or Cl2. Something which is very, very polar is something like HF. And then something which is polar enough to actually ionize itself is something like NaCl. Okay, right, sodium chloride. So covalent character is on a spectrum, it's on a continuum. It can go more or less covalent. And one end of the side you have covalent, and on the other end you have ionic. Lastly, for this section, we're going to talk about when you do have polar bonds, how symmetry plays a big role. So as you can see here, this is a symmetrical molecule. So this goes back into your VSEPR theory where you're looking at shapes. Because of the linearity of this molecule, it goes in a straight line, and this is 180 degrees. It's a perfectly symmetrical molecule. So even though there are polar bonds, there is equal amount of pull on the electrons going that way as there is going that way. We can show this with this little symbol here where they have a positive sign on one end and a negative sign on the other. Overall, we can say there is no net dipole. And what that means is there is no overall pole because they cancel each other out in effect. They cancel out. However, if we suddenly have an asymmetric molecule like water with polar bonds, suddenly, because we have the electrons being pulled up towards the oxygen there and up towards the oxygen there by the polar bond, suddenly overall we have a negative end at the top and we have a positive end at the bottom. And this is what we call a net dipole that arises because of the symmetry. So there is a net dipole, and that means overall dipole. And that's because it is asymmetric this time. So symmetry is really important when you're looking at polar molecules. It might very well have a polar bond, like the carbon dioxide, but it doesn't mean it's a polar molecule. In the next video, I'm going to show you how to work out the trends in the different intermolecular forces.